With the definitions out the way, we're now in a position to state what Benedixson's criterion actually says. So let's say we have dynamical system. X dot is f of x, which lives in R2. In other words, x is a two-dimensional vector and f is a two-dimensional function of x. And we also need that f is continuously differentiable. Then suppose that either divergence of f is positive everywhere, or divergence of f is negative everywhere. In other words, if divergence is not zero and has the same sign everywhere in R2, in that case, the system has no invariant simple closed curves. So that is to say, no periodic orbits, or any of the slightly more complicated things. So also no homoclinic orbits. So none of these. No homoclinic orbits. And no heteroclinic cycles. So things we saw with the finite amplitude pendulum. So Benedixson's criterion is a way of showing that there's no periodic orbits in the system. So let's consider an example. So we have two ODEs, dx dt is x cubed and dy dt is y cubed plus y plus x. So if we're going to write these in vector form, then my vector x would be x, y, and my vector f would be f, g, where f is x cubed and g is y cubed plus y plus x. And what I need to do is check the divergence of f. So divergence of f, that's just df dx plus dg dy. So in this case, That's 2x squared. No, it's not, it's 3x squared plus 3y squared plus 1. So that's 3x squared plus y squared plus 1. So the first term, this is positive everywhere except the origin where it's 0. And this term makes it positive everywhere. So div.f is greater than 0 everywhere in R2. So that means there's no closed curve trajectory systems. In particular, no periodic orbits.